In this video, I'm going to do a quick introduction to the periodic table and how to navigate the periodic table. So remember, the periodic table shows us the elements, where elements are pure substances from which all other things are made. And so elements cannot be broken down into simpler substances. So they can be broken down into things like electrons and protons and neutrons, but those things are not elements, so those do not belong on the periodic table by themselves. We need atoms for something to actually be considered one of the elements. And so elements are identified by their chemical symbol, which is the letters that you see on the periodic table. So these are 1 or 2 letter abbreviations for the name. The first letter is always capitalized, and the second, if there is one, is always lowercase. So for instance, if we have a 1-letter abbreviation, then it's always capitalized. So carbon is capital C, nitrogen capital N, fluorine capital F, hydrogen capital H, and so on. Whereas if we have 2 of them, then the second letter is always lowercase. So for instance, cobalt is capital C, lowercase o, nickel is capital N, lowercase I, selenium capital S, lowercase e, thorium capital T, lowercase h. But some of the chemical symbols actually come from the name of it in Latin or Greek, and so you might see things like this, where potassium has the letter K, that comes from the kalium. Iron is capital F, lowercase e for ferrium. Tin, capital S, lowercase n for stannum. Copper, capital C, lowercase u for cuprum. And so those come from Latin or Greek names. So that's why some of the elements have letters that don't really seem to correspond to what the name of it is. That's because we're using the names for them from another language. And so the periodic table organizes the known elements, and we will talk in later videos more about why it's organized the way that it is, but for now we're just going to discuss what the organization actually is. And the start of the periodic table was first developed by Dmitri Mendeleev back in 1872, and back then they didn't actually know what a lot of the elements were, but they were able to predict what some of the other elements were based on the periodic table. So for instance, if you didn't know what like polonium was, you would be able to have predicted some of its properties based on where that would actually end up in the periodic table. And so that's one of the strengths of the periodic table, is not only that it helps organize a lot of these things and make sense of some of the trends that we'll talk about in later videos, but it did actually let people predict what other elements there would be. And so these are arranged by things like mass and properties. So as you go left to right, top to bottom on this, then they are increasing in mass, and as we'll see in later videos again, there are certain properties that have trends on the periodic table. And so each horizontal row is what's called a period. Masses of the elements generally increase across the period. So for instance, the top row is the first period, the next one down is the second, then third, fourth, and fifth. Then we have the 6 there, and remember that this lanthanide series actually belongs in this green spot right here, so that is actually part of the 6th period. So we don't want to put that into the table. It's usually kind of left off to the side or below it, because otherwise the periodic table would become extremely wide without being very tall, and so that would make it a lot more unwieldy to put into an image like this. And then we have the 7th period, where, again, remember the actinide series is part of the 7th period there. So we want to make sure that we're putting those in their proper spot when we're thinking about what periods these elements belong to. The vertical columns are called groups, and they're arranged the way they are because elements that are in a particular column have certain properties, especially chemical properties, that are similar to each other. We'll talk more about that in future videos, so the way that they actually act in chemical reactions or in bonding with other things are very similar when you are in a column on the periodic table. So the way that these are arranged, we have first what are called the main group elements that are given the A designation here. So we have the 1A, the 2A, and then we jump over to there to get to the 3A, then 4A, 5A, 6A, 7A, and 8A. So those A ones are called the main group elements, but then we also have what are called the transition metals, and so that is these ones here that are called the B group. So we have 3B, and it's 3 because it comes after this 2 right here. Then we have 4B, 5B, 6B, 7B. Then all three of these are called the 8B group right here. Then we jump back to 1B and 2B. And quite often the periodic tables will actually have the columns listed like that. So you can actually see on this one it does have those listed, but I put these on here so that they're maybe a little bit bigger and clearer to see. So like I said, we have these different groups here. Some of them are given special names. So for instance, the first column, at least all the stuff below the hydrogen anyway, are called the alkali metals. The next one is called the alkaline earth metals. And then we have the halogens that are over here in the group 7A. Then we have the noble gases, which are in the group 8A right there. Then I've already mentioned this, but these ones are called the transition metals, these ones that are in the light blue right here. Then those two rows that are sort of taken out and put down below are called the rare earth metals. And so those are special names given to some of these. And we can split up the periodic table based on whether something is a metal, a non-metal, or something in between called a metalloid. So for instance, all the stuff in red on here are metals, and then all the stuff in blue on here are nonmetals. And then we can see sort of the dividing line right here in yellow, where those are the metalloids, where metals are things that are shiny solids at room temperature, except mercury, which is a liquid at room temperature. They're called ductile and malleable, where ductile is essentially that you can sort of squeeze something down and sort of roll it in your hands until you sort of stretch it into a wire. If you think about taking like a ball of Play-Doh and just sort of rolling it back and forth in your hands until it turns into sort of a tube structure, metals you are able to do that with. Malleable just means that they are bendable, so you can bend things that have metal without them just cracking and breaking. And they're good conductors of heat and electricity, and they tend to have high melting points. Then nonmetals are not particularly shiny, ductile, or malleable, so these are things that will usually just crack and break if you try bending it too much, and you can't really roll it into a tube like you can with the metals. They tend to be poor conductors of heat and electricity, and they have lower melting points. And then the metalloids are things that share properties of both of them. So, for instance, metalloids are better conductors than nonmetals, but worse conductors than metals. So that's why silicon, for instance, is used as a semiconductor in computers, because it's a semiconductor because it's not a conductor the way metals are, but it's not a resistor the way that nonmetals are. And so silicon can be used as a semiconductor because it is a metalloid. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.